Hello. So, in this video, we are going to be talking about how to solve equations that have radicals in them. So, for example, what if we want to figure out the values of x that sort of make this thing work, right? Make this equality true. Well, up to this point, right, we've really hammered in, okay, we can't do anything with multiple terms. So first step, we got to factor this thing. But we can't factor this thing, right? So like now what do we do? If we can't factor it, what do we do, right? That was always step zero. We always had to factor it. Well, because this is an actual equality, not just an expression, right? I have that equal sign. I can actually sort of go about this a different way, which is that I can try to undo the radical by using the inverse functions property, right? Like we're used to using radicals to undo powers, but we can do powers to undo radicals. So that's the sort of technique that we're going to try here. So to remove the square root function, we're going to use its inverse, the square, right? So I'm going to look at this. I'm going to square both sides, right? So I take the square of the square root, and on the other side, I take the square of that whole side, which in this case is just 2. And that gets me that the square and the square root undo each other, right? So I just have that x squared plus 4 minus 1. And on the right, I had 2 squared is 4. But now this thing looks like a polynomial, right? I can move the 4 over. Now I have a thing I can factor, so I can factor this as x plus 5 and x minus 1. And that gets me that x is negative 5 and x is 1 are my solutions. And in fact, I can plug these in, and it turns out, everything works. Okay, so great, right? We just do a nice power and move forward. What could possibly go wrong? Right? Well, again, math, that's what can go wrong. So let's look at a similar example. So in fact, I'm going to use almost the same example, right? So we have the same sort of setup, square root of x squared plus 4x minus 1. Can't simplify that, like I can't factor that anyway. And now I have it equal to negative 2. Well, I can't factor it, but again, I have an equality, so I could do the same thing, right? So I'm going to, right, because I can't factor the radicand, again, that's almost always sort of a good starting spot. I'm going to instead, just like before, use the sort of inverse function, right? So since I have a degree 2 root, or a square root, I am going to use a degree 2 power, or a square, to undo it, right? So I square both sides. Well, on the left, I'm going to lift the radical, right? Meaning I get rid of it. The radical and the square undo each other. On the right, negative 2 squared is 4. Cool. Well, again, now I'm looking at a polynomial, so I can move the 4 over. Voila, I have something that's factorable. Factor it up. X plus 5, x minus 1 equals 0. That gets me that x is negative 5 and x is 1. Those are solutions. Not so bad, right? Perfect. Yes, this is a trap. So let's look at those values, but let's plug them in and see what happens, right? So here I have that x squared plus 4x minus 1. I want it to be negative 2. So if I plug in negative 5, that was one of my solutions, I think. So if I plug in negative 5, well, I'm going to do negative 5 squared plus 4 times negative 5 minus 1. So that's 25 plus negative 20, or minus 20, minus 1. So that's 4 inside the square root. Square root of 4 is 2. Well, that's maybe not great. So, okay, well, let's try the other one, right? So we want to try 1. That was the other one we solved. So 1 squared plus 4 times 1 minus 1. So that's the square root of 4, which is 2. Which is still not great. So what gives, right? Did we make an error? I mean, we could go back, and feel free to go back if you want. We could go back through and see what we did, but there wasn't an error anywhere. Like we did step by step, everything worked out. We didn't do anything wrong, but still we got answers that aren't answers, right? They don't work. So what gives? How is it that we can get answers that aren't answers? Well, here's the big asterisk to this process. The problem is that we applied a power other than, 1, right? Like we actually did something to both sides. And whenever you do that, sort of in any context, you run the risk of sort of introducing these things that are sort of valid solutions, but not sound solutions for any of you logic geeks in the crowd, meaning that they are things that we sort of structurally solved correctly. We didn't make any errors along the way, but we still didn't end up with a correct answer. So these things have a special name, and these things are called extraneous solutions. So extraneous solution is a solution, right? Loose quotes here. It's a solution to something, to like an equality or whatever, that you sort of acquired through a perfectly valid process, some solution method like we just did, but at the same time, it doesn't actually work. It doesn't actually satisfy the original problem, okay? So extraneous solutions are basically results that you get through like not making any mathematical errors along the way, but nonetheless don't work. Now, if we think about it, and in fact, I'll even go back a step here. If we think about it for a second, there should have been a bit of a red flag right at the start. So give it some thought here and maybe pause the video and see if just looking at the question prompt, you can figure out why it is that any solution we would have come up with almost certainly couldn't possibly be right. Okay, so hopefully you thought about it, paused, or whatever, but I'm going to point out that we have on the left of the equality a square root. And the whole thing about a square root is that its output, right, we can only do sort of positive things in there if we're using real numbers. And the output is always non-negative, right? It's always 0 or higher, but we're claiming it equals a negative value. That's downright shady, right? Like it can't equal a negative value. Square roots can't be negative, right? So really there was sort of a big red flag right at the start with this particular problem. Unfortunately, not all extraneous solutions are that easy to see that that's going to be showing up, but this is sort of a nice thing to notice right off the bat, okay? All right, so that's extraneous solutions, but let's look at another problem. So now let's look at this sort of radical, equation with radicals in it. And again, the idea here is like 3x minus 2, you can't sort of factor that any more than it is, right? It's a linear polynomial. Those are already fully factored. Same with x minus 1. The only hope we have of sort of solving this, meaning like actually getting x values, is to do the sort of thing we did before, where we're going to try to undo those squares. So the first step, and really I claim the first step, but really this is one of those things you just want to do periodically between steps if you happen to see an opportunity, is to simplify anything that can be simplified. Because the more you sort of smash down numbers, the sort of less terrible they become. Because when you're squaring stuff and you have a big number and then you square it, it gets really big. And if you have to do that more than once, you are going to be very sad, right? So any chance you have to sort of divide out numbers cleanly, it's a good idea to do that so that sort of in the future when you're taking powers or whatever, you don't end up with really big things. So here I notice, okay, well, 3 goes sort of, I have a multiple of 3 everywhere, so I can just divide everything by 3. And now I get down to just that 3x minus 2 plus square root of, 3x minus 2 plus square root of x minus 1 equals 1. Now, the next step I want to do, I want to isolate one of these radicals. I want to have a radical of stuff equals whatever else. And that whatever else may also have a radical, but the sort of hope is to have just a radical on one side, okay? So here I can do that by subtracting over that square root of x minus 1, right? If I subtract square root of x minus 1 from both sides, now I have that 3x minus 2, the radical, right? The square root of 3x minus 2, I have that on its own side, and then that equals the negative square root of x minus 1 plus 1, okay? Now, step 3, we're going to apply sort of the correct exponent to both sides, where in the sense the correct exponent is whatever sort of undoes the root. Here, this is a degree 2 root, right, a square root. So I'm going to use a degree 2 power. I'm going to square both sides. So when I square the left, I'm doing that to undo the square root. Now, strictly speaking, there's some absolute value craziness happening here, but we're sort of not worrying about that part. And in fact, that's sort of where the extraneous solution bit is sneaking in the background. So instead of having to deal with absolute value craziness, because it would get real crazy real quick, we're sort of going to ignore that part of it. But that's also why we have to check solutions at the end. That's sort of the thought bubble in the background here. So step 4, we need to expand everything and then combine like terms. Now, on the left, that's not really a problem because like we said, it's going to undo, right? Each piece is undoing each other. But on the right, this is one of those things where students sometimes miss the forest for the trees kind of deal, where they're so focused in on trying to do the radical part of it that they forget about the binomial expansion, meaning you have to actually distribute this whole thing out because there are middle terms you have to use, right? You can't just do the first thing squared and the second thing squared. You also have the cross terms and the middle stuff, right? So FOIL, box method, distribution, whatever it is you like to do. Doing that on the left, right, the radical and the square undo each other. We just have that 3x minus 2. On the right, we end up with x minus 1, and I have a plus 1, but I also have this minus 2 square root of x minus 1, okay? So that's what you get if you sort of FOIL everything out or whatever. So after I've done this, combine like terms, right? So I put together in this case, the constant on the right is really the only thing I can do, where I have the plus 1 and the minus 1, they cancel and leave me just the x and the minus 2, whatever. So once I've combined like terms, I sort of simplified it as best I can. Well, if I still have radicals, I basically rinse and repeat, right? I go back to the idea of, okay, if I still have radicals, isolate the radical, use an appropriate power, etc., right? So I still have a radical here, that's square root of x minus 1. So I'm going to isolate that by subtracting x from both sides and then dividing by that negative 2. Or, and I'm sort of pointing this out here, if I divided by the negative 2, it would actually go in evenly, right? So I can divide by negative 2 here, it would work there, it would work over here, and it would work over there. But if I don't see that, right, which is what I'm trying to show here, if I don't see that, I still get the right answer. The only difference is I'm going to end up with bigger numbers along the way, right? So if I had divided by 2, I'd have like a negative x plus 1 squared, and that would give me pretty nice numbers. On the other side, that negative 2 I wouldn't have to worry about. If I don't do that, I have to be a little careful, but it'll still work. So on the right side, because these things are being multiplied, I square both, right? So negative 2 squared, that gets me 4. Square of square root of x minus 1, those undo each other, and I just get the x minus 1 on that side. On this side, I have to expand everything out. So I get 2x quantity squared, which is 4x squared. I'm going to get a minus 2 squared, that's the plus 4, and then I'm going to get 2 times negative 2 times 2x, which gets me that negative 8x. So again, FOIL this out, box method, distribution method, whichever way you like to do it. That's what you should get as a result. Now, once I have gotten rid of all the radicals, right? So now I have no more radicals. Now I sort of just proceed to solve however I need to solve, right? So in this case, I have a polynomial, so I'm going to solve it like it's a polynomial, right? Move stuff off to one side. To do that, I'm going to sort of expand out on the right, distribute the 4 so that I can move everything off over to the left, and that gets me this 4x squared minus 12x plus 8. I might now see that I could divide everything by 4, which really was dividing everything by 2 up here, but I squared it. That's why it's now divided everything by 4. So this is what I would have ended up with immediately if I had divided everything by 2 up here. Regardless, now I have x squared minus 3x plus 2. That's nice and factorable, x minus 2 and x minus 1. So I know that we have the solutions x equals 1, x equals 2. Right? Finally got there. Almost, right? So again, we have to be careful because we got answers, but we did take powers of both sides. In fact, we did it twice. So we do have to check the extraneous solutions, right? So step 7, we have to test all of the solutions to verify which ones actually work in the original equality. And it's really important here that we use the original equality and not one of the steps we had along the way, because we have to make sure that it works at the start, not during the solution process, right? So here, for example, we could test x equals 1. So if we plug that in as x in our original equality up here, we get 3 times the square root of 3 times 1 minus 2 plus 3 times square root of 1 minus 1. That's the 3 times the square root of 1 plus 3 times square root of 0. Square root of 0 is just 0, right? That's perfectly fine to square root. It's just 0. So that gets me 3 times 1 plus 3 times 0, which is 3. Great, right? That's what we wanted. Now, the other one we got was 2, right? So same idea. We're going to plug in 2, see what happens. So I can plug in 2, 3 times square root of 3 times 2 minus 2 plus 3 times square root of 2 minus 1. Simplify that down. That's 3 times square root of 4 plus 3 times square root of 1, which is 3 times 2 plus 3 times 1, which is 9. 9 is definitely not 3, right? So here, this is not a solution, which means that x equals 2 is actually an extraneous solution. So here we solved it, and it wasn't that both answers worked or both answers didn't work, which is situations we saw earlier. Here we had 1 and 1. So really they can be sort of mixed together in our solution results. Okay? All right. So step 8, and our last step, keep the answers that work, right? So x equals 1 was a valid solution. X equals 2 was not. We keep x equals 1. Great. So 8 steps. I will sort of go through them quickly here, but there's really an easier summation version of this. So step 1, which is really step x.5, right? Do it periodically whenever you see a chance. Simplify anything that can be simplified. Divide by numbers, make them smaller so that you're dealing with smaller numbers. Step 2, we try to isolate a radical on one side. So if there's more than one radical, just pick one, doesn't matter which one, and isolate that one. Step 3, use whatever exponent undoes that radical. So if it's a fifth root, use a fifth power. If it's a third root, like a cube root, use a cube. If it's a square root, use a square, right? Use that on both sides in order to remove the root on the isolated root. Step 4, expand everything and combine like terms, right? And make sure that you're distributing things correctly because you may have binomials and you want to make sure not to lose the middle terms. Step 5, basically check to see if all your radicals are gone. If they're not, go back to step 2, isolate whatever, pick another radical, isolate it, and proceed, right? Once they are all gone, step 6, right? So now we process the resulting equality however it is that you need to solve it. So typically you'll probably end up with like a polynomial, so you solve it like any other polynomial, get everything to one side, factor it, and find the zeros, right? Step 7, now that we've done that and we have applied powers at some point, we have to test all these solutions to verify whether they're actual solutions or whether they are like those extraneous, like false solutions. And step 8, keep the ones that work, right? Like obviously we don't want to use the extraneous solutions. So you can memorize all of this. It's very thorough, let's say, very sort of nitpick all the way down. But the general mantra is much easier. The mantra is, if you have a radical, isolate it, then undo it. Keep doing that until you've gotten rid of all the radicals. Solve the resulting thing now that you have no radicals, and check your solutions. Keep the ones that work. Okay? So, what did we do? Well, we talked about how to deal with radicals where we honestly can't factor them, right? Like step 0 of everything that we usually talk about is factor first, can't do anything unless it's factored. But there are times where you still need to solve it even if it can't be factored. And if it's an equality, right, you have two sides of an equal sign, there is a way to do that by using these powers to undo roots. The downside is that can get sort of algebraically messy, right, expanding stuff out all over the place, especially if you have larger roots, right? If you have a cube root or a fourth root and that you have to undo, you're looking at expanding out, a binomial to the fourth power. That is very obnoxious, or can be very obnoxious. And the other side, sort of the more insidious part, is that it also introduces the potential for extraneous solutions. So whenever you're having to do it this way, where you're undoing roots with powers, you have to check your solutions to make sure they actually work, because you could make no mistakes and still end up with a wrong answer, right? Or an answer that doesn't work, okay? So that is that.